Hey, how's it going, guys? So today I'll quickly go over the question clone graph of LeetCode 133 question. Okay, given a reference of a node in a connected undirected graph, return a deep copy of the graph. Each node in the graph contains a value integer and a list of its neighbors. Okay, and there's some something that tells you about the test cases. So you can see the example is, and the output is really confusing. The example, we're given like a adjacency list, right? And we output also a adjacency list. But in our signature of the question, we actually are given a node and we have to output a node. So this question is really poorly stated. What the question really asks is that if you have a graph like this, and you are given an entry node, let's say the entry node for this graph is 1, then you have to output a new copy of the original graph and output the entry nodes. So if your entry node was 1, you have to output the 1 as well. Yeah, so it's not actually inputting a adjacency list and outputting an adjacency list. It's actually inputting a node to the graph, and output a node to the graph. Yeah, so this is very confusing. The second confusing part is here in the signature. It says self.neighbors equals to neighbors. It doesn't say whether it's a list or something, but if you go back to here, it's actually the neighbors as a list of node. Okay, after clarifying this, the algorithm for this question is actually using BFS, using Q, and creating a map. And so the map will map the old node to new node. So for example, if you have old node 1, the key will be the old node and the value will be the new node 1. And why do we need this map, right? It's not very intuitive, but let's say if you have a copy of the graph, you have a copy here. So how do you know which node is the entry point? Right? You do a DFS or BFS of the graph and you get the new graph copy. And how do you know 1 is your entry, right? You lost track of that. And the reason we do a map is because when you somehow get the graph, and all you need to do is to return the node. So basically, you have your old entry node as node. So all you have to do is return d node, and that will give you the new graphs, new 1. Yeah. So yeah. So this question is not intuitive at all, and is kind of confusing. But I hope you find what I was saying helpful. So let's take a look at the code. So first of all, you check the corner case if the node is empty. If there's no graph at all, then you just return none, right? You don't have anything. And then these are just the template for BFS, right? BFS is using a queue. And if you're not familiar with BFS, then you should probably go back to the BFS traversal first. So basically, BFS is using a queue. So I initialize as a deck, so double-ended queue. So and I append the node into the queue, and I create the dictionary. And this is just a template, right? While the queue is not empty, I pop my node from the queue, and I call it current. And what I do is I have to create this map, old node to new node map, right? So basically I'm saying this is my old node, right? I'm creating a copy of the node. So node current.value, you will give me a deep copy. Okay, and again, this is just a template for BFS, right? For neighbors in current.neighbors, if neighbors is not in the map, I also create the old node to new node map, right? So the neighbor equals node neighbor.value, and I append the neighbor to the queue. Again, this is just a BFS template, right? After you processing like say 1, you have to process 2 and 4, right? And then you again we have to create a new graph. So we not only care about the value of the node, we also care about the neighbors, right? So our current node's neighbors. So this is our copy of the current node. It's new current node. Its neighbors. Again, it's a list, right? So you append the new this new neighbor node to it. So that's why we do this line. And at the end, we just need to return